Simple pendulums. A simple pendulum is one in which all of the mass is considered to be a point mass and is located at the end of the string, i.e., the weight of the string is negligible. In addition, the angle of displacement of the pendulum must be small, no greater than about 15 degrees. Let's label these quantities in the figure. There's the mass of the bob, m. We are displacing this a distance x. The length of the pendulum is L, and we have an angle here, theta. So for a simple pendulum, the huge fraction of the mass, a huge fraction of the mass has to be right there. And that angle theta is going to have to be less than about 15 degrees. So let's draw a free body diagram of this bob when it is at the position shown. There's the bob right there. mg is going to act straight downward, and then the tension is going to act at some kind of an angle like that. And those are the only two forces that act on this mass. Letter D. In the free body diagram, break mg into components parallel and perpendicular to the bob's velocity. Let's see here. Parallel to the bob's velocity, we would have an mg component that would go in that direction, and perpendicular, we would have a component that goes in that direction. Let's do the perpendicular component. If I drew that in there, there it goes. And what would that be numerically equal to? That would be numerically equal to mg, and let's see, if we look at the angles, if that's theta, then theta would be right in here. Theta's right in there as well. So mg cosine theta is what that one is. And that one, of course, is the direction that is perpendicular to velocity, because the velocity is going to be acting at right angles to the tension always. The component of mg that is parallel to the velocity, I could draw it down here, right there, but I'm going to draw it up there like that. The parallel one is going to be mg sine theta, like so. Moving on. How does the string's tension compare to mg cosine theta? So let's look at the picture one more time here. How's the tension compared to mg cosine theta? Well, according to the picture, the tension is greater, which it is, but that's not how we know that it's greater. The way we know that it's greater is that there's a centripetal acceleration on any mass that's moving in a curved path. And so there has to be a net force toward the rotational axis. And that must mean that the tension, in this case, at that instant, has to be greater than mg cosine theta. Let's determine the acceleration parallel to the bob's velocity. We could call it A parallel. We need to look at our free body diagram. There it is. And in the parallel direction, the only force that's in the parallel direction is mg sine theta. Well, that's kind of nice. All right. Well, that means for Newton's second law, F net equals mass times acceleration. The net force is mg sine theta, and that should equal the mass of the object times the acceleration parallel to the bob's velocity. The mass cancels. That means that the acceleration parallel is equal to g sine theta. Letter G. What type of acceleration is that? Is that a centripetal or is that a tangential acceleration? Look at our picture here. It's definitely not centripetal, because centripetal would be pointing towards the center of the path. I'm going to have to circle tangential there. Based on the definition of the sine function, modify part F. Well, what's the sine of theta? Let's look at our picture here. Isn't the sine of theta x divided by L? We could modify our earlier answer to look like that. Part H, which we just did there. Part H involves a tiny bit of hand waving because x and A parallel are not quite parallel for every position of the bob. But as long as theta is small, then the approximation is good enough. Anyway, we need to add a negative sign to part H. Do that. Okay, let's do it. It says we're supposed to do that, so let's do that. Add a negative sign. Either side of the equation, it doesn't matter. And then say why we need to do that. Well, we need to do that because x and a parallel have opposite directions. You can see in the upper right corner, if we displace this mass to the left, isn't this bob going to have an acceleration to the right? Similarly, if we displace it to the right, the acceleration will be to the left. So we throw in a negative sign there into that equation. Now, letter J. Previously, we found that for simple harmonic motion, the acceleration is equal to the opposite of omega squared times the position. When we were doing our simple harmonic motion equations, that is what we found. Let's put this into part I and see what that gives us. Well, if acceleration is opposite omega squared times x, then on the left side, I'm going to put opposite omega squared times x, and then on the right side, I'm going to leave it as is, opposite gx over L. X cancels, the negative sign cancels, omega is equal to square root of g over L. Lastly, substitute an equation we derived previously into part J and solve for period. If omega is equal to the square root of g over L, and omega is 2 pi divided by the period, we learned that a few videos ago. If we solve this for period, what does that give us? 2 pi times the square root of L over g. You might have seen that equation before. That is the equation for the period of a simple pendulum. Notice that the mass of the bob does not affect the period.